Hello, everyone. Welcome. Thanks for joining our diagnostic training session today. And what you're about to see is a pre-recorded training session we did over in the United States. But be assured that a lot of the material that we cover is really applicable to any automotive application. So just be aware that yes, it is a lot of North American vehicles, but they will apply a lot of the same principles apply over in the UK as well. Now, if you do have any questions, if you're watching this during the premiere, you can just leave it in the chat. We'll be monitoring live chat. If you're watching this after the premiere, then just feel free to leave a comment underneath the video and we'll get to those as we can as well. So my name is Jason Gabrenas. I'm one of Snap-on's diagnostic technical trainers. I've been in the training department since 2013, traveling around North America, helping techs and shop owners get the most out of their diagnostic equipment. Before I did that, it was a couple years as a diagnostic sales rep at Snap-on, so I had 30 different franchisees I worked with, as well as the shops that they serviced, in order to help everyone get the most out of their diagnostic needs. Then before I did that, it was 8 years at Subaru. So I worked in a dealership, and over time, I guess, just became the default diag guy in the shop. So I always ended up having the drivability problems, the intermittent problems, the weird wiring problems that would show up on those cars. And that's really where I cut my diagnostic teeth, was trying to figure out all those weird head scratcher type cars that would come into my bed. Then before that, a bunch of other miscellaneous wrenching jobs. Been a little over 25 years under hood experience for me. So our topic today is auxiliary emissions systems operation and testing. So this is it's going to be a wide variety of different auxiliary emission systems that some manufacturers put on their vehicles. Some manufacturers don't use them. Some manufacturers use them on a couple models only, and some manufacturers just use them on all models. So it's a bunch of different auxiliary emissions affecting drivability affecting type systems, but you're not going to see them everywhere. You don't see them on every vehicle, every manufacturer, and really it's stuff that we don't have. It's not really much to talk about for half an hour, so we put them all together, kind of give you one good class all together with this. So the EGR valve, we're going to talk about the air pump, variable runner intakes, tumble generator valves, and displacement-on-demand systems. So first off, we're going to talk about EGR valves. Now, this has been used on both diesel and gasoline engines for quite some time. And what it does is it's used to reduce cylinder temps, which in turn reduces NOx emissions. Those oxides and nitrogen, very bad for the atmosphere, not a good emission. So try to reduce that as much as possible. Now, really, it seems to be more of a problem on diesels than it is on gasoline engines at this point. But they do use them both on gasoline and diesel engines. It can vary from fully open to fully closed, and we have a range of motion in between there. And then it can also be vacuum or electrically operated as well. So here's just a vacuum controlled EGR valve. So you see they operate fairly the same way. We have the exhaust comes out, goes through the exhaust manifold, tapping off the exhaust manifold goes in the EGR valve, which stands for exhaust gas recirculation, and that's exactly what it does. It takes the exhaust gas and then recirculates it back into the intake manifold, which in turn cools the combustion chamber. Now, in this case, it is vacuum operated, so we have a vacuum line that comes into the solenoid. Into the solenoid, we also tap vacuum off the intake manifold, so depending on how far this is open or how long this solenoid is open, because it can be pulse width modulated controlled, depending on how long or how much it is open is going to depend on how large this diaphragm opens. So the diaphragm is attached to this pintle, which pulls it off the seat. If it opens a little bit, we get a little bit of exhaust gas flow. If it opens a lot, we get a lot of exhaust gas flow. Pretty similar to the way it works on an electronically operated EGR. So in this case, they call it a stepper motor. Also, in this case, we have an EGR cooler in the way, so we don't have the hot exhaust gas hitting this electric solenoid. It's going to cool it off a little bit before it gets there. The ECM controls opening and closing. Also, many times there is a position sensor in there as well to give feedback to the computer as to see how far it's open and closed. So there is my recirculation there. Same type of principle, just instead of vacuum, it runs off an electric DC stepper motor. So here's just a closer look at the two types. We have a, like I said, the vacuum operated here, pulls up on the diaphragm. The diaphragm is connected to this tapered pintle and the pintle seat. So the exhaust comes in and it flows by the pintle and the exhaust goes out. If I open a large amount, a larger passage allows more exhaust in. Smaller hole, smaller amount of exhaust. Just depends on how much vacuum is allowed in there and how much is allowed past the seat. Over here, we got the electronically operated one. So we have an electrical connector on the top, which gives us positive and negative, plus the position sensor feedback is in there as well. In this case, the position sensor pretty much works like a throttle position sensor, where it's a variable voltage output depending on the resistance. We have the electromagnet around the outside, the windings for the motor, and it moves the pintle up and down based on pulse width modulation usually. Once again, we have the pintle seat here where it seats in the hole. If it's closed, then no exhaust gas gets through. If it's open, then the exhaust gas gets through and goes into the intake manifold. Now, that being said, due to that design, we have exhaust gases flowing into this EGR valve. Depending on how dirty that exhaust gas is, we can have some problem. We can have some carbon buildup and soot in this case. Probably more common on diesels just because the exhaust is inherently a little dirtier before it gets through all the catalytic converters and stuff. So inherently on a diesel, more than likely it's going to be more often to clog, but it can cause problems on gasoline vehicles as well because the pintle sticks on the carbon. You can also have a failed relearn due to carbon, or maybe you'll have a relearn that didn't fail. At least as far as the computer is concerned, it didn't fail, but it can cause a problem. I'll give you an example. We'll go back to this drawing of the electronic EGR valve. So if I want to relearn this, what we're going to do is going to be a functional test, and the computer is going to basically pulls it full open to full close. Maybe cycles it through a couple times just to get the distance to travel. When it's closed, according to the computer, that is closed. That is 0. That's where I'm going to close it, and I don't want to go anywhere past that. So if I open it, and then when it opens, maybe a little piece of carbon falls in there. Gets stuck right in here where that little red arrow is right there. So maybe I got a little piece of carbon on there. And then it closes and it sticks on that carbon, so it can't close all the way. It can't make a complete seal. But if that happens during the relearn, then the computer thinks, oh, well, that's closed with that little gap. And then maybe it opens again, that piece of carbon falls out, goes into the exhaust, goes into the intake, wherever. And then when it closes again, well, it's never going to seal because according to the computer, well, it's not fully closed. Well, fully closed is partially open, if that makes sense. Whatever the distance of that little piece of carbon that was holding it open before, even though it's gone, that now allows a leak. So my EGR valve is going to leak in that case. Now, you can fix it by just doing it. Well, you'd want to clean it first so it doesn't happen again, but you can clean it and then reset it and relearn it, and it'll be okay. Oftentimes, that can be the case, and it could cause a drivability problem because we're going to have vacuum being in places where it's not supposed to be and exhaust in places where it's not supposed to be at times when it's not supposed to be there. So just keep that in mind. If it's an electronically operated EGR valve and you think maybe it might be dirty, it might be worth cleaning and relearning before actually replacing the whole deal, because it could go through its whole distance of travel, but might have been contaminated when it did the relearn. I've actually seen that happen a few times, so something to look out for. Next emissions system, air pumps. So air pumps have been around since the 60s. So they used to use them on big V8 cars and whatnot. What it does is it adds high pressure air to the exhaust. By doing so, we are adding additional air to the exhaust, essentially leaning it out. And then that allows the cat to reach temperature quicker because we have more oxygen content, allows it to light off faster, and allows it to get up to temp faster. Can be either belt driven. On the older ones, they're belt driven, or on the newer models, newer vehicles, they can be electric. It's kind of like this one over here. It's just a electric motor with an impeller on there, and just outputs some high pressure air. So here's the old school air pump you might be used to from back 60s, 70s, 80s. You would get the smog pump, air pump, whatever you want to call it. We got the pulley there, it goes on the pump. Pump's just got some impellers inside, and then it got a couple valves here as well. But then we had these pipes that would screw into the exhaust manifold. Remember that? It would be like right at the top of the manifold. You'd have these different pipes that you had to screw in there. And I remember selling these back when I was in a parts store, and we had the, I need a smog pump for this, or I need a air injection pipe for this. So they were definitely around, and obviously replacement parts are available, but they would have failures, of course. And that's the old way we used to do it. And then the new way we do it now is with an electric air pump. So in this case, this is off a Subaru. We got the electric air pump there. It's got some hoses. It kind of splits. And then on this case, it is for both banks because it's a horizontally opposed engine. It's got 2 banks of cylinders. So for each bank, we have these valves, which operate on a pulse width modulation, open and close. And then we have the metal pipes that go down in the back of the exhaust port in the cylinder heads before it gets to the exhaust manifold. So through here, we can get soot, we can get clogging. We can also get water intrusion within the pump, within the valves themselves. They can become damaged, corroded, rusted shut, things of that nature. So think about condensation in the exhaust. Condensation can get in there. And then when it just sits there and it doesn't have any way to heat up or evaporate, then it just kind of sits there and it ends up rusting, corroding, what have you. Common codes that would relate to this, not necessarily the solution, but would relate to this would be a P0410 or a 411. It's due to flow on the secondary air system. Here's a couple examples I found. This one's a corroded valve. You can see how I got a lot of rust and crud in there. And then on this side, that's one of the pumps. And you can see we got a lot of water intrusion in there, a lot of rust and just general not good stuff in there for an electric motor. So that can cause the motors to seize. It can cause the valves to seize. It can cause all sorts of issues with it. I had to replace tons of these on Subarus. The valves would seize. And of course, the valves are not an easy place to get to either. They're like halfway underneath the intake. And the metal pipes that came off them had metal gaskets, and the metal gaskets were very, very thin and razor sharp. So that was always fun too. Actually had to come up with a tool to take them apart without having to take the entire engine apart with that. A couple swivel sockets and a swivel extension, and we can get in there and get them out pretty easy without having to take them apart. But yeah, we replaced enough of them where we had to come up with that. So fairly common, at least. I don't know, maybe it's just my part of the world. It's wetter or something. Maybe in the desert it won't happen. I don't know, but can happen just due to the moisture in the exhaust. Next one's variable runner intake. So there's multiple versions of these that multiple manufacturers have used. And what it's going to do is it's going to change the intake air path, the path that the intake air takes. So at low RPM, we want it to take a longer path so we get a stronger pulse on the low end. In this case, this has 3 levels. This is on the BMW's DISA system. So low RPMs has the long runners. Mid-range RPM, we put some medium range runners in there as well. And it can also get the back pulses off the intake as well. And then at high RPM, we have the shortest runners of all right in there, and allows everything to flow much faster and allows it to do that. So that's 3 stages. That's what they use in their DISA system. They also had a DIVA system, which is a little earlier than that, actually. And this was a continuously or infinitely variable runner intake. So it has these chambers in here for each cylinder. It kind of looks like this. And what happens is there's a center shaft and a motor. And that motor can turn it anywhere from the longest it's set for to the shortest it's set for, and anywhere in between, infinitely variable depending on the load requirement of the vehicle. So you could have a very long intake runner, you could have a very short intake runner, and anywhere in between. Only limits your imagination, put it that way. So the ECM, whatever the ECM wanted. So that was a variable runner intake. So it's just, once again, stepper motors and position sensors in that case. Related to that is tumble generator valves. So what these do is they increase the amount of swirl in the intake system. It's usually used at low RPM, idle. Combustion increases the combustion efficiency because we have increased swirl in there. Also increases low and mid-speed torque because we're mixing the fuel better. So airflow comes in the normal case with the valve open. There's a butterfly valve right there. Normal cases just comes in through whatever on the intake and does its thing, normal thing, like it wasn't even there. When we close the valve, you see that it's got like a separate partition coming in this intake plenum, and it's accelerated up through the smaller hole. So a larger volume of air going through a smaller hole increases tumble, and it allows it to swirl a lot more when it gets inside the intake valve. Now, this is off a Hyundai. Hyundai has a system like that. I know Honda Acura had one. I had a 94 Integra that had a system like that. It was a big fat intake manifold that had 2 sets of runners, and then they just had a set of butterfly valves that would open and close depending on which one needed to go. So that was a fairly simple system. Subaru, we dealt with that for a long time. Started with when they first started turboing the cars in the early 2000s. Looked like a intake manifold step up type thing, or like a plate that would raise it up. And inside the plate, we had the butterfly valves that would open and close. They would close except for that little tiny spot. There's a shaft that went through the butterfly valves. There's a motor on one side, and then there was basically a throttle position sensor on the other side. That's how that worked. On the older versions of that, what would happen is it would happen only at cold and only at idle. So if you started the vehicle and just let it idle, the tumble generator valves would be active, would be increased tumble in there. When it finally warmed up, they'd open up and that'd be it. Or if it wasn't warmed up yet and you just stepped on the accelerator pedal one time, they'd open up and they'd stay open. And then, of course, on the newer versions, what they did was they would open and close until it was finally warmed up. Even if you stepped on the throttle, they'd open, but then they'd close back down when they needed to. So it was able to open and close on the newer generations. Here's just another example on the Hyundai of how that system looks, how the system works. So they call it a variable charge motion actuator. And these are the components of the system. So we have the motor itself, which is an electric motor with, it looks like it's got some gear reduction in there. Connecting rod, a couple arms here. And then you can see where that goes in the intake plenum right there. And then at the end of the intake plenum, we have the butterflies right there, or the flaps. They'll flap up and then it'll seal off the bottom part and allow air to go through the top part and swirl. So that is just a couple simple tests. Does the motor work? Does the position sensor work? And does it mechanically work? Easy enough to check. And then lastly, before we get live on the tool, we're going to talk about displacement on demand. So depending on the vehicle, a couple manufacturers use this. They'll cut out a certain number of cylinders on larger engines. So if I have a V8, usually it cuts down 4 cylinders. On a V6, like the way Honda does it, you can either run on 6, 4, or 3 cylinders, depending on how many they cut out. No matter how they set it up and how they make it work, the overarching goal is increasing fuel economy at cruising speeds. Because if you think about it, I'm just on highway, part throttle, 5%, 10% throttle, not even doing anything, just coasting. I don't need 8 cylinders worth of power. I don't need 8 cylinders worth of fuel being dumped in there and burned too. So it reduces the amount of power that's, power is not required, put it that way. We don't need the power. So we're just going to shut off half the engine so we don't have to burn too much fuel. That was their whole idea behind it. So this is how Honda's works, and it's pretty much the same idea with anybody else who uses it. At idle and during hard acceleration, I want 6 cylinders because at idle, I'm probably going to be accelerating, so we'll just leave it in 6-cylinder operation. Once I get up to a cruising speed, I don't need that much, so we're going to cut out half the engine. We're going to just do 3 cylinders. When I coast a little bit, I go into fuel cut. Don't need anything there. And then I'm also cruising here, part throttle, stick to 3 cylinders, going to decelerate again, get down to idle, turns it back to 6 cylinders because the computer knows, well, if you're idle, probably going to accelerate again. So we're going to run on 6 cylinders. Accelerate, go up here, 3 cylinders. Then in this case, we want to accelerate even further, but we're already going maybe 60 miles an hour and we want to accelerate to 70. I don't know, 55 to 70, whatever it happens to be. Not a huge acceleration. So we go from 3 cylinders and then we go to 4 cylinders in this case, and then we'll just cruise there for a little bit. And then I'm sure it probably knocks it back down to 3 cylinders. Just depends on the logic of the computer. So that's kind of an interesting way that they show it here as a graphic. We want to look at the engine system. Now it has both high lift and low lift cams because it runs VTEC. And if you want to learn more about the VTEC system, we have another class on that. The variable valve timing class also deals with that. So there's a couple different cam lobe profiles that it uses. And the cylinder cutout system works very much on the same type of idea, the same type of principle as the VTEC system as a variable valve lift. So it can shut off cylinders on demand. So in this case, this would be 6-cylinder operation on this Honda. Then we're only showing one bank, but it works the same way. We have rocker control arm valves, control solenoids, and so on, and it runs all on oil pressure. On the default state where it's just running normally, all 6 cylinders, we have these springs. And we have pins on the rockers. We got bunch of set of rockers in there. There's like three sets of rockers per cylinder, at least. And what it does is it locks them together. When it's normal operation, all the rockers would be opening and closing the way they're supposed to. When we cut it down to 4 cylinders, it's going to cut out the back 2 cylinders. So number 3 and its companion cylinder on the other side. What happens is runs oil into that one, pushes the spring over, pushes the pin over. Then this rocker is now running not attached to the cam. It's just sitting closed because the valve springs will keep the valves closed. And the other side of the rocker is just going to sit there as an idle and just follow along with the camshaft, but it's not going to open the valve. Same thing on this side, it pushes the pins in and they just sit there free. The rockers don't actually move. For 3-cylinder operation, it's going to shut off this entire bank. So we send oil pressure to all of the cylinders and all of the pins, and then it just lets them all loose. So the camshaft's basically just freewheeling there and nothing's opening. And I'm sure it also shuts off the fuel and all that because it knows, the computer knows what it's trying to do. So it shuts off the fuel, shuts off the spark, shuts off the valves. And really, it just literally shuts down the cylinder so nothing happens. In that case, we don't have any air going in, we don't have any air going out. I'm sure they probably open it just a little bit so it doesn't have a pressure in there, but it's enough where it just shuts it off. So that's how it works on an overhead cam engine like a Honda. Now on GM, the way they do it on like their Vortec engines, those are still pushrod engines. So on the pushrod engines, we have these roller lifters here. And the roller lifters have pins and springs, just like they do with Honda. It's just a little bit different. So in this case, the springs push out on the pins and it's locked in place. So in this operation, it's opening and closing the valve. Here's the outside portion that we can see. So it's not a cutaway. And then there's where the oil passage is. When they want to shut down the cylinders, it will put oil in here, push against the spring, release these pins. Now the outside part of the rocker can move independent of the inside part of the rocker or the lifter. So within that case, we're just pushing up on the outside and the push rod stays in place. The push rod doesn't move. In this case, the push rod is locked in with the outside, so it's going to move up and down. In this case, it is not locked, so the outside moves separately from the inside, which allows it to shut down that cylinder and not open the cylinder. So this is kind of the older way that they would do this at GM. This is how they started with displacement on demand. Now, newer models, they went to what they call dynamic skip fire. So what this will do is based on computer inputs and outputs and loads and whatever the computer's programmed to do, it will decide to skip cylinders in the firing order depending on what it needs. So if I only need 4 cylinders, it would maybe do every other cylinder or something like that. If it's on a low demand scenario, we won't fire every cylinder. If it's on a high demand scenario, we'll fire every cylinder the way it's supposed to. So every once, depending on where it is, and it's active, it depends on the load. The computer makes all the calculations on the fly and turns the cylinders on and off on the fly as well. So that's kind of an interesting way of doing it. Read up on that. Also an interesting note with vehicles like this, and this could come in handy to keep in the back of your mind if you're thinking about working on a vehicle with this. So there are vehicles that even though they're supposed to have it, don't have it due to the chip shortage that we've all been dealing with right now. GM couldn't get chips or enough chips. Talked to a guy at a Cadillac dealership who said, yeah, they can't get enough chips to make the processors for this system. So that's the first thing they dropped. So it actually came out with a whole new RPO code and everything that doesn't have the displacement on demand system in there. So that I guess if they decided one module is going to keep this truck from getting off the factory and going to the sales lot, then I guess the one thing we can remove is that displacement on demand system. So they did. So there will be vehicles that come through year, make, model, supposedly would have it, but according to this special RPO code and the way that it's equipped, doesn't have it. So you could be trying to diagnose a problem. It's like, oh man, it must be a problem with the cylinder cutoff system. And it's not, because it doesn't have it. Right? So I just wouldn't want you to go down that road as well. It's like, oh yeah, this it's got to have it, but maybe it doesn't have it. It just depends on the vehicle, especially when you're coming into the 2021, 2022 model year. That'd be something to look out for. Just an FYI. All right, let's go live on the tool and look at a couple examples of some tape. All right, first vehicle is a 2017 Toyota Tundra with a V8. So first I want to look in guided component test. So if you have a tool with the guided component test function, there'd be any Snap-on tool with a lab scope function in it. So a Triton, a Modus, a Vantage, a Veris, a Verdict, a Zeus, any of those tools have the guided component test database. So I'm going to load this. It is vehicle specific information. In this case, I want to look in the engine system and see what we can find. This has a couple different things that we talked about already in this class. So first off, air injection. We go into information about the air injection system. In order to reduce cold engine emissions and warm up the three-way cat quicker during cold engine operation, engine coolant temperature between 41 and 104 degrees Fahrenheit, an air injection control system has been added to this model. Secondary air injection is supplied by a DC electric motor driving an impeller. Air injection control driver controls air pump under direction of the ECM. Clean air enters the pump through the air filter. Downstream of the air pump, pressurized air enters two electrically controlled air switching control valves with pressure sensor. When ECM command switches air switching control valve to open, air is supplied to each bank through air injection port in the exhaust manifold. Air injection pressure and exhaust gas pulses are monitored by the air pressure sensor, and the sensor may also be called a turbo pressure sensor. So then we have the air pump, the valves, and then the secondary air pressure sensor. So the air pump itself, pump is activated by the ECM to add oxygen to the exhaust stream on startup. This assists with warming up the catalytic converter faster. Electric air pump consists of a DC motor. Rotation of the impeller pressurizes air, then supplied to the air injection valve. Electric air pump is part of the air pump assembly. Assembly is located behind the right rear bumper area. It can be accessed by removing lower front fender liner in that area. Air pump on the left side is for bank 1, right side is for bank 2. So it has two pumps for the two banks. And then we have our connector views, and then we have our pin assignments for that as well. And then down here, we also have heaters and powers and such like that. And it tells us where it's located and where the best place to test it is as well. All right there. So I back up, there's a functional test that we can do. Continued air pump functional testing can cause pump overheating. Limit testing to no more than 4 attempts at 5 seconds each with a 30-second interval between tests. So if we're using a functional test to turn it on, turn it off, we don't want to run it too much or it's going to overheat. And then we have a resistance test here as well. So it's going to say connect the red and blue leads. And then at the whatever temperature it is, ambient is what our resistance should be on that air pump. Then we have the valves themselves. So solenoids using the air injection system to allow or block air traveling from the air injection pump to the exhaust stream. The use of the solenoid replaces the prior use of conventional check valves. Air switching valve is an electrically controlled valve that is used to open and shut air pressure between electric air pump and exhaust manifold injection tubes. Gives us the look as to what's going on here. So we got power, ground, sensor signal because it's got an air pressure in there as well. And it also has the sensor itself, ground in there. It's got a position sensor as well. So you can see that, a couple different ways to do that. And then once again, a functional test is going to talk about how we're going to functionally test them, make sure they open and close. And then the resistance test should be 4.5 to 5.5 ohms at 68 degrees with that valve. So really it's an open or closed type situation. Secondary air pressure sensor is going to give us a voltage test that we can do. Key on engine off should be 3 to 3.6 volts. On a pressure pump, apply it to a 0.5 PSI. Key on voltage should change as pressure changes. So that's going to be your pressure sensor in there as well. All right. And then we also had in here intake manifold runner control valves, so actuators and solenoids. So this has vary the intake runner length based upon engine load. So we have an intake runner control valve. Solenoid right there. We have a DC voltage test we can do on that because we have pin assignment as well, 12 volts of ground. Should hear the motor operate if we momentarily make or break the connection. And then we have a resistance test we can do too, 37 to 44 ohms at 68 degrees Fahrenheit. There's a lot of good information there in the guided component test. Then if we go to scanner, let's look at what we can actually. So that'll be under the engine, of course, and we'll go into actuator tests. So in this case, we have intake control for the intake control valve, the variable intake. Is an on and off. And then we also have secondary air injection system, so we can do a manual or an automatic check. So if I go into the automatic check, it determines malfunctioning parts in the air injection system, used to identify the components that may cause a malfunction or validate a repair of the air injection system. So this does two important things for us. First thing it does is we're going to verify a failure, which is what we always say to do. And then also after the fact, it will verify that it works after I do a repair. So that's important too. So you can go to continue. In automatic mode, it'll just go through and simulates the system monitor. Manual mode, you have to step through them manually. You're going to confirm the vehicle is stopped and the engine is idling. You're going to continue. I'm going to get an error here because I'm not plugged into a car. Got to wait 5 seconds. Okay, there we go. The scan tool couldn't activate the air pump or the air switching valve. In this case, well, it's because I don't have a vehicle hooked up to it, so it has nothing to actuate. But it would also go through and say either passed or failed and gives you the codes. Manual, same thing. So that's air injection. Let's go look at tumble generators on a Hyundai Santa Fe. So that's under engine again in the guided component test. And then we have the tumble generator actuator and sensor. So the actuator is the one that's going to turn it on and off. Tumble generator system utilizes an electronically controlled butterfly valve in each intake runner port. At cold idle, the tumble generator system will redirect the air charge through a different port. These ports have a finish characteristic, pardon me, finish characteristic that causes the air-fuel mixture to swirl and tumble greatly and create better combustion. This results in greater idle quality, cleaner emissions, and easier cold starts. All good things. And it tells it when it turns on. So we have the motor actuator and the sensor signals as well, all in one connector. So we can take a look and pin out at that connector if we need to. DC voltage test, key on, voltage should be approximately 1.8 volts. And then for the position sensor, should be 1.7 volts at idle up to 3.2 volts for closed to open status. So it's going to be just like a throttle position sensor. We want to see it go closed to open, nice and easy, nice and smooth. Let's see what else on this. I think that's the only thing on this. And then if we go into the scanner, see what we can do in that. Engine functional tests. And we see there's a ton of functional tests in here. Electronic throttle control, variable intake solenoid. There it is right there. And what that's going to do is that's going to be an on-off situation. So start and stop. I'm going to move it, or it's going to go back home where it was. So that's just a simple on-off functional test. We can do that as well. Last thing I want to look at is a Impala. Actually, I got two more things to look at. So Impala, that has an EGR valve with a position sensor that we can test. So if we go in here, we go to EGR system, and we go to component information. It's going to tell me about the EGR valve. Receives ignition for EGR control. PCM uses pulse width modulation on the EGR minus to obtain desired pinto position, and the EGR is pinto position sensor to monitor actual pinto position. So it's a 5-volt sensor, 3-wire. DC voltage test, that's going to give me my EGR valve opening and closing, so we can actually simulate that. So it should go 0.5 volt to 5 volts with no dropouts or glitches. It's going to be very much just like a throttle position sensor on a vehicle. So in this case, it's open a bit. I'm going to go down to that 0.5 volt. And then we would sweep it open and close. You sweep it up, sweep it down. Should see it go 0.5 volt up to about 5 volts. Fully open to fully closed. Now what happened is if I had it closed and then I went to open it and this happened, I had some glitches. That's a dropout in the sensor. That's a bad EGR position sensor, and I would want to get that removed. You could have just like a flat spot in it, just like on a throttle position sensor, you could have a flat spot in it with that as well. The other test that we can do here is going to be a duty cycle test. So this will tell us the duty cycle opening and closing the EGR valve. So if I hit view meter, it's going to give me an on-off percentage time. So in this case, I'm looking at 60%. If I go this way, brings me all the way down to like no percent, up and down. This one's being a little weird too. My other board was being weird earlier in the day too. Let's see. Normal. There we go. So it's going to measure your duty cycle Maybe this will help. No, it will not. Okay. There's my duty cycle. So I can see it going up and down as I barely move this thing up and down. So right now we're at what looks like a 50% duty. So what if I wanted to cycle this back and forth and see how it reacted using the scanner? Well, I can do that too. So I can go back to my scanner. And go to my engine functional tests again. On GM, they like to call that output controls, where I'm going to take over one thing at a time. And then we have the EGR percent. So it's just an up and down. So if I can go up to like 50%, I should be able to see that reacting on the scope as well with a 50% duty. So all I got to do is I'll leave this going. If you have a Windows-based tool, you can do this at the same time. Other tools, you got to flip back and forth. So on a Windows-based tool, if I'm back in the component test, I can go up to meter, make it full screen, go to meter again, turns it into a window. And go back to my scanner, pull up my test that I never left. The test is still going. Come down here, pull up my taskbar. I can see my scope. I can move that over there. I can move that over there. And then I can move it up and down as I need to in order to see how my test goes. So if I bring that up to like, say, 70%, I should see it go up to, of course, my board is being funky tonight. Okay, let's say it went down to, 25% or 30%, right? Yeah, this board's being really wonky tonight. Anyways, so you would be able to see it go up and down on a working vehicle. Now, if it was being erratic like this, you definitely have a problem somewhere in the circuit as well, because that duty cycle is not doing what it's supposed to do. So that's a good example of a not good pattern. Not good at all. Being really weird. It should just be fairly straight line, and then as we go up and down, you should see it follow up and down as well. And this is a different scope tester too. Very strange, very strange. All right, so that is my time for our oddball emissions stuff. And with that, that is our time here today. So make sure you tune in for new diagnostic content every week. We will be premiering a new video every Wednesday at 7 p.m. UK time. So make sure you check it out on the YouTube channel. If you're watching, well, of course, you would be watching this on YouTube, but make sure you subscribe, thumbs up, ring the little notification bell so you know anytime we post new content. And it's youtube.com/SnapOnDiagnosticsUK. With that, time for questions. If you have any questions, just feel free. Once again, if you're watching this on a premiere, just leave it in the live chat and we'll answer those. Otherwise, leave a comment under the video and we will get to those as we monitor those comments as well. So I'd like to thank you for taking a little bit of time out of your day to learning a little bit more about how you might be able to be more efficient at diagnosing vehicles using some of the information that we've given you today. Hopefully we'll see you next week. Hopefully you can watch and see you on any of our other videos. Have a good week, have a good night, and take care.